basically from the civil engineering background, but I will try as much as possible to suit this lecture towards civil engineering. So some of the examples that I take in this lecture might be more familiar to you than me, but let's see how we can take simple examples and clarify some of the very fundamental concepts of machine learning. Okay, now there are four things that we are going to look at during this lesson today, and in the initial few minutes, we are going to look at the theoretical aspects of machine learning, and then the next half of the lesson we'll dedicate it to understand what data actually means, how we can prepare good data set, and what sort of things that we need to do. We are going to learn the concept of feature engineering and how we can clean a data set, those kind of things which are essential when we start machine learning in any domain. In any domain, those are the main aspects that we have to do. So it's thank you so much everyone for joining the lecture at this time. Let's start. Right now, since you have already done few things during this course, and you might have already have an understanding why should a civil engineer care about data, machine learning or AI? Is their purpose? Now, if you take there are different domains that we can think of: electrical and electronic engineering, mechanical engineering, likewise civil engineering. Why we need to care? Now, civil engineering is gathering a lot of data. Now, that is one thing compared to many other fields. So there are a lot of data that are coming fast. So civil engineering gather a lot of data. So you need to analyze these data to take decisions. That is one of the main reasons that we can think why we need to use machine learning in civil engineering applications. For example, in the traditional setup, as I see, you get the data, you analyze it through certain laws, probably in tabulated format, like you have rules, these are there. So you analyze them using those tabulated rules again and again and again, take decision. So when you have this kind of data set, probably you might be able to automate some of the decision taking aspects. As an example, here look at there might be sensors on bridge and dams, like 10 to the power 6 or 10 to the power 9 samples per year. So you can check the health of the bridge in your dams using this data. But in traditional setups, you need to analyze this data in certain manner. You will use definitely some tools, classical tools, but still you need to analyze them. Can we do something instead using machine learning? Now, for example, everyday concrete batch plant looks mixed proportions and 28 day streams. So you might be more familiar with these things better than me. But those things generate data like traffic loops and GPS traces in traffic engineering. Those kind of things are there. So when you have data with you, machine learning is a tool that we can consider always. So because machine learning is all about fitting flexible mathematical models to data so that we can predict, classify, and compress or decide exactly the things we already do with the usual regression, but with far few assumptions than we had earlier. So you can see that that's a key word here: fitting flexible mathematical models. So we'll see what that means later. But look at what we can do if we can have a machine learning model. We can predict, we can classify, we can compress, we can take decisions. Those are the things that we did earlier using classical methods. So we can, instead of using these classical methods, probably we might now be able to do it using machine learning. Now, what's the advantage of doing that? The advantage is you'll probably make very fewer assumptions than earlier, and probably you'll do it very fast as well. So you have different advantage. So that doesn't, you can see that it doesn't mean that for every application, machine learning is the solution. It is not. We'll see later. But for some applications, by having this machine learning as a tool, it will do a very good job. So when we talk about machine learning, we need to see where it actually fits in this setup. Now, there are few words that you need to understand properly first. Probably you have already done these things, but for a refresher, probably we'll understand it again in a different perspective, probably. Now, the main thing that we come across again is a set of words, terminologies, like artificial intelligence, you'll have machine learning, you might have, then neural networks or deep neural networks, deep learning. Those are the words that are coming from this domain. So we need to understand what are them first. Now, if we start with artificial intelligence, it's all about building systems that replicate the intelligent behavior. So any system that replicate the intelligent behavior belongs to this category. So a very broad umbrella. That means it's the largest set out of all. It includes handwritten rules, search algorithms, and involve no learning at all. Some algorithms, there might be search algorithms that involves no learning at all, but still they belong to artificial intelligence or AI. So handwritten rules, as an example, a rule-based code checking tool that verifies clause by clause compliance with in a certain civil engineering application is still a AI because it replicates the intelligent behavior. Anything that replicates intelligent behavior belongs to that category. Now, in that a artificial intelligence umbrella, you'll find a subset as machine learning. It's a subset of AI that learns to make decisions by fitting mathematical models to observe data. Now, this is the key difference here. If you apply machine learning, you need to do these things. You need to fit a mathematical model to observe data. So you must have data. You have a set of data on your hand. Now, what you do, you are trying to fit a mathematical model so that you can see patterns. You can achieve certain goal. So therefore, if you do this, to replicate the intelligent behavior, then it's a machine learning algorithm. You are again replicating the intelligent behavior, but how this intelligent behavior comes? By fitting a mathematical model to observe data, rather than by being explicitly programmed with rules. So we don't use rules. Rules are at the end of the learning process, there might be a set of rules that you can see, but it is not the purpose actually. The purpose is the rules also will be seen, identified during this process, fitting the observed data to the mathematical model. So as an example, fitting this compressive strength against cement content, water content, and age over 1,000 batch records. So you have records of data of water cement, the content, and what your objective is to fit a model to find the compressive strength. So that's a learning task because you don't have any other thing. You don't have to consider about rules or any other things, but what you see is your data, the cement and water and the compressive strength, how it changed, and now you try to find a model. That model will replicate an intelligent behavior. So therefore, it belongs to artificial intelligence. Because we are using data and because we are building a mathematical model to fit the data, it's machine learning also. So it belongs to machine learning. So every machine learning algorithm is a AI. But every AI is not a machine learning algorithm or machine learning method, right? So that's the main difference between AI and machine learning. Now, then the word that we hear a lot is deep neural networks. Now, this deep neural network is one particular family of machine learning models. It's because we can fit this data in to a mathematical model in various ways. We can fit because our objective in machine learning is you have a set of data, you need to find a mathematical model to fit. But that fitting can be done in different ways. This deep neural network is one particular way of doing that. So that's the most popular method that we have. One particular family of machine learning models built by composing many simple parametric functions, which we'll see later in this course, right? Deep learning is what we call it when a deep neural network is the model being fit. Deep learning means this process of learning, like process of learning how to fit this model. So these few words are very important because you will come across these words again and again and again in any domain that you are working. So therefore, a clear understanding about these things will be really helpful. Now, if you look at this relationship, you can write this deep learning is the smallest subset. Then you have machine learning. On top of that, you have artificial intelligence. So machine learning is not a synonym for neural network. Those things we can discuss later as well. Okay, so I hope these definitions are clear. If you have any questions related to this, please post. We can discuss on the go. And if we depict it in a picture, we can see that artificial intelligence is the largest set. Then inside that we have machine learning. Now this machine learning means fitting a model to that given data. You can do that fitting in three different ways. You can learn that model using three different manners. One is supervised learning, the other one is unsupervised learning, the last one is reinforcement learning. So our objective in machine learning is learning the model based on the data. You can learn in three different ways. One is supervised learning, the other one is unsupervised learning, the last one is reinforcement learning. Right. In supervised learning, the way we do it different to the unsupervised learning, and it is entirely different to reinforcement learning. We'll see how these three methods work in later slides. Right. Now, deep learning is applicable to all the three domains. That means deep learning is one family, particular family of this machine learning technique. So you can apply supervised learning in a deep learning manner. Unsupervised learning also you can do deep learning. If reinforcement also you can do deep learning. So if you apply reinforcement learning in this one, deep reinforcement learning is the result. So this is the picture that you might remember as a summary of everything. So we'll discuss about supervised, unsupervised, and reinforcement learning and introduce them briefly in the later slides. We can discuss them. Right. Now, if we quickly have a look at before formally learning about these three things later, in supervised learning, now what our objective, we need to keep our objective in mind. What's our objective? We have a data set and we need to fit a mathematical model to that data set. Now you can do that in supervised learning. I think that's mic turned on. Okay, right. Let's move on. Now, so in supervised learning, you have inputs and matching outputs as the data. So you have a data set where you have an input and you have output. Both input and the output is given. So based on that input and output, you are trying to predict something. As an example, let's say that you have a data set like this. Let's say there's a data set with age, maybe age, and let's say height, and you need to predict probably weight, something like that. This is just a simple example, weight or something. Weight, something like that, probably. Now you can see that you have maybe hundreds of data points for a different age, height. When you give that, you estimate weight, that kind of a data. Now, since you have both the inputs and the outputs on your hand, that's a labeled data set. That means you have a label. You have every time, for example, here you might have entry age is, let's say, 5, height is, let's say, I don't know that, let's say 70 centimeters, and weight is, let's say, 22 kilos, something like that. So you have a data set. Now what you need that one, by using this data set, the inputs and the output relationship, you need to build a model so that when someone gives you an unknown entries, for example, let's say age is 50, weight, height is, let's say, 130, something like that, and you need to calculate weight on average, right? You need to calculate. So that's an example. So that kind of a task we call supervised learning. Why? Because in your data set, you have a data set such that you have the inputs and the outputs both. You know the inputs and outputs for the given data set. Now, what you do is you train them and find a relationship. Now, this example is not that good because usually we don't do something like that, age and height and weight kind of things. It's much sophisticated sometimes, but just to understand these things, it's enough. And one other example, a simply more simplified example you can see. For example, if I give you a pattern, for example, let's say X and Y, I have one input, one output. And I have an input data set like this, 1, 2, 3, 4, let's say 5, something like that. Then Y is, let's say, 2, 4, 6, 8, and 10, let's say. Now, this is the data set that I have. These are the inputs, these are the outputs. But by looking at this data, if I ask you what might be the output for, let's say, 20, you might very straightforwardly say that the output is definitely 40. Because in your mind, you can easily get the relationship. Relationship is pretty straightforward here. That is 2 times x. That is obviously true. Now, this is what we mean by fitting a model actually. In our mind, we ran a process and came up with y equals 2x. 2 times x is the model. So this is the model actually that we try to build. So this is the data set that we use. But what we did here was kind of supervised learning. Why? Because you can see the inputs, you can see the output. So you can see the pattern between how this input has been related to the output. And in your mind, you do the calculations and you find with 2 times x. Okay, now this is very simple. Now let's say instead of doing that one, I'll make this, let's say 2.1, 3.3, probably this is 5.9, 8.1, probably this is 9.7, something like that. Now what? Now, in your mind, you can see that. Now I'm asking what's the output for 20. Well, you need to find that. That's the task here. Now you can see when it is 1, when the input is 1, the output is 2.1. When the input is 2, it's roughly 4.3, something like that. Now, you can see that if you look at carefully, probably the output might be 2 times x, but probably it might not. Probably it might y equals 2.1 times x, probably is better approach. Or else 2 times x plus 0.1 might be the model. Now you can see that here, when the example, when you have thousands or millions of data in a setup, it's not easy to find this relationship quickly. You cannot get that. So we need a method to do that. That method is this learning process. Learning process means finding this best mathematical model. Probably this might be y equals 2 times x plus 0.1. Maybe that may be not. Now, how we get that? Through learning. Learning is the process. Through learning, we'll identify what's the best model that fit into this data. So that is about supervised learning. Now, how to find this model? How do you find? In your mind, in the early example, when the inputs are exactly y equals 2 times x in the early example, what you did, you tried to find a model so that the loss between the predicted ones and the actual variables are less, as small as possible. That means what? You have an actual y and you have a predicted y. What you try to do is the difference between the actual y and predicted y, you try to minimize it as much as possible. In the earlier case, this difference was 0. So that means you don't need actually learning algorithm, because you can find that relationship. But here it is not the case. For example, if you look at this model, what's the predicted model and what's the output, there's a difference. For example, in the first instance, there's no difference. That's the error is almost zero. But you can see if you look at this point, this is 4.3, but from the model, what we get is 4.1. So there's a difference between 0.2. So you can see that there's a difference. In the third example also, there's a difference. What we try to do in learning to reduce this difference between the actual and the predicted one as small as possible. We'll try to do that. And there's on top of that, there's something called generalization. Come, let's discuss them later. But to understand what is this learning process, I think this simple example is good enough. That means this is the learning process. This is what actually, if the number of data entries are small and if the input data set is pretty small, probably we can do it by our hand as well. But when the data is pretty large and the patterns are very sophisticated, and say that this y is dependent on not only in one variable, maybe it depends on the several hundreds of variables. If that is the case, then it will be really tough to do it in a classical manner. So that's why this learning process is required. So you'll hand over the process of learning it to the algorithm. So it eventually converges to a point where it gives us this relationship. So machine learning model means nothing else, this equation, right? Whatever the equation that you find ultimately is the model. So model means this equation. So our ultimate goal is by using the data, finding this equation. So as we said earlier, this equation we can find in three different manners. That is, one is supervised, the other one is unsupervised, and third one is reinforcement based. Right. Now, I think the supervised learning, we'll discuss it again later, but for the moment, I guess this idea is clear. Supervised means you have a labeled data set, that input and output both you have. Sometimes you cannot have both input and output at hand. You might have only inputs on, right? There's no labeled data, as an example. So in those, most of those setups, what our task is actually not predicting some number, it's predicting some structure or a pattern, identify a pattern of something, identify a pattern. So the main question is, what does the data look like? It's the cluster. For example, you can group the two data into two categories probably. Likewise, those kind of clustering examples come in mostly in that area. So if you look at examples for supervised learning, like predicting this compressive strength from mixed proportions, is the bridge photo cracked? You have a set of photos, you need to decide whether it's cracked or not. Predict flood depth from rainfall and catchment features. Those are some examples of supervised learning where you have both input and output. But look at here. Now, clusters of 500 CPT logs into soil units. Find three dominant modes of bridge vibration data. So you have data, now you have to divide into groups. Some of these things I don't know actually, this internal mechanism, because I'm not directly from civil. But these are examples of doing it. So you can see that this belongs to somewhat pattern recognition. Like you don't have our input-output relationship, but you have a data set that you try to find patterns. Now, both these input, the supervised and unsupervised, are working with this loss function, something called loss function. That means you try to minimize the mismatch between your model prediction and the actual data. There's another way that we can learn. There's another way, that is reinforcement learning. Actually, all human beings learn in their life mainly through reinforcement learning. Actually, supervised, unsupervised, and reinforcement learning are connected to our lives. We learn anything from these three. That's nothing else. You will see that, right? Now, reinforcement learning is somewhat different to other two. So it acts based on a reward. So learning algorithm attempt something based on the result, you'll get a reward. you'll get a reward. As an example, if it's like this, say that you are riding a bicycle. Now, when you are riding a bicycle, there are few actions that you need to take. That means you ride at certain speed, or accelerate, or brake. Those are the actions that you have to take. You turn left, turn right, those kind of actions you have to take. Now that happens on the go itself. By observing the environment, you have to take a decision. You do it. How you do it? You try to ride without any harm, without falling. That means your reward, you are expecting a reward. If you take a bad decision, what will happen? You will fail, or you will fall down, and something bad can happen. So therefore, what's your goal, end goal? To navigate without any harm. That's the reward. To achieve that reward, you can navigate. Probably you can have some other goals as well. You might navigate from one point to the other point as quickly as possible. Those kind of things also can happen. But it's based on reward. So if you do something good, you'll get a better reward. If you do it something bad, you'll get a bad reward. So as an example, chess game. In a chess game, you take certain actions during that time. By looking at the reward that you probably will take a move, so that you'll expect a better reward in future. So it's a reward-based setup, a reinforcement learning. Actually, all in our younger days, we learn through reinforcement learning. We learn walking actually through reinforcement learning. You'll try, and you'll figure out a better way to do it. For example, say that a very young kid, like one and a half years old, starts walking. He will try different methods. He try and try fall, so that inside him, he finds a method ultimately so that he can walk. After finding that method, it's easy because you have to follow that method. So no one actually teaches that. Even in swimming, you can get some advice, but you have to try and find a method that works for you. So most of our activity is actually reinforcement learning. Most of the learning comes reinforcement learning. So reinforcement learning is another method of doing that. So in there, you learn a policy, you learn a method, you learn a policy, so that you can take action to maximize the long-term reward. We can discuss about them as well later in the course. Now you can see that in supervised learning, for example, in a class or a tuition class or a school, you might do some tutorials, right? You will do tutorials together with your teacher. So probably you do hundreds of examples very similar. But you do that, you do this question and you have the answer, this question and the answer, question and the answer. So you train. If you get a similar kind of question later, which you don't know the answer, but now since you have the practice of earlier learning, now you can provide an answer. Those kind of things are examples of supervised learning that we learn through those experience. So you can see that supervised, unsupervised, and reinforcement learning paradigms are quite different methods for different applications. So you have to first choose, therefore, in your application, when you try to apply machine learning, the first thing is you have to decide which method suits more, whether you go for supervised learning, unsupervised learning, or reinforcement learning. That's one of the initial decisions that you need to take. Because sometimes supervised learning might work perfectly for your application. Then you don't need to try for the other. Sometimes supervised learning will not work at all because you cannot have labels. Then you might go for unsupervised learning. So that's a decision the person who builds the system has to take always. And implementation-wise, supervised learning is easier than unsupervised, and reinforcement learning is a little bit harder to implement as well, right? So, for example, this adapting traffic signal timing at the junction, you have to take decisions then. So most of the time when you have to take a decision, you go for reinforcement learning. Okay, so do I have the right answer for all set of past cases? If you get an answer yes, in that case, go for supervised learning. So if you have data set and if the answers are correct, then you have to go for supervised. If no, but I have lots of inputs, then you have to go for unsupervised learning. If I must act repeatedly and get delayed feedback, then reinforcement learning is the one. So usually in reinforcement learning, uh, get the reward later. We take the action now, but we'll get the reward later. If, for example, think chess game, you take a decision and act now, but the reward comes later. So similarly, now this is just a brief overview of the three learning paradigms that we are going to look at. Now, one thing is that this machine learning is not a black box at all. If you apply maths and inside, you can easily understand what's going on in the model. For a very simple application, like if you have 2, 3 variables as the input and probably 1 or 2 outputs, you can actually visualize what's going on. But when you have more and more variables, its visualization is tough. That's why people kind of think it as a black box. It is not a black box at all. It's all maths going on. Maths, it's maths. So it's basically linear algebra, calculus, and probability that runs in a mutually supportive manner. So that's why we can try to understand a little bit about what is inside this model and what we mean by the model. But I'm not going to go into very high level information here because that is not the purpose in this lecture. Now look at what happens here. Now we have a model. We have a model. Right, that's a question in the chat. Let me check that. If I know I have wrong answer for half of the set of the cases, what is the learning I should use? That's a question that we can discuss, and it's an important question as well. That's all about the data set. So if you don't have a correct data set, you cannot do anything. So therefore, we can discuss about that in the second half of the lecture. Thank you so much for the question. It's a important question to discuss. We can keep that question in mind and discuss in the second half. Right. Thank you so much. Likewise, if you have any other questions, please post it here so that we can discuss them on the go. Right. Look at what happens here now. We have a model. Model means a mathematical equation, nothing else. It's a mathematical equation that we are trying to learn. Now, to the mathematical model, what we input, these are the model inputs. We input a set of data. Now, in this example, we input the water cement ratio as an example. So we need to input that number. We'll see how we input them. We are going to discuss about feature engineering later. Now, let's assume that we input this number to the model. Now, model is a function, mathematical function, which has variables and parameters. There are two things. Now, x is a variable. Now, phi is a parameter. These parameters are the one that we are trying to learn. Let's say now, after doing some mathematical manipulation, you will have a function in your hand. Now, when you have a function, getting the output is pretty straightforward, right? If you have a function, for example, let's say I have a function fx phi equals 2 times x plus 1. This is the answer, right? Model that answer. So if I give you this 0.55 to this function, then you can get the output as 2.1. So you get the answer. That's straightforward once you have the model. So how to get the model is the question. To get the model or this function is the learning process. We'll see an example here. Now the model is nothing more than a mathematical equation y equals this with parameter phi whose values were chosen by looking at data. So phi is the one that we trained during the learning process. That means phi is the number that we need to figure out. Now look at an example. Let's say that we have a large set of data here, word cement ratios. Now you need to find this compressive strength as the output. So your task is to find the relationship. Now, by simply applying all the inputs and outputs, you will try to figure out a model where the mismatch between the predicted value and the actual output is very small. Now, this is the model that we have chosen. We have chosen a very simple model, phi naught plus phi 1 times x is the output. Now, what we do? What we do is we'll try to figure out phi naught and phi 1 so that the difference between predicted value and the actual value is small. So here x means water cement ratio, that's the input term. So you can see that if but this is what we did in earlier our simple example as well. For example, when we have x and y, 1, 2, 3, 4, let's say 5. So 2, 4, 6, 8, and 10. When we have this, what we did is pretty similar. So f equals now phi naught plus phi 1 times x. So in the first instance, 2, I'll write it in a more clear manner. First, in the first, if I enter this first number, so output is 2. So the 2 equals this phi naught, phi naught, phi naught plus phi 1 times 1 times 1 is the first answer, first question, equation that we get. Then the second equation is 4 equals again phi naught plus phi 1 now times 2. Likewise, you can write these 5 equations. Now what you need to figure out what's the best phi naught and phi 1 so that the difference between the predicted and the actual ones are less. Now, by doing that, and after doing this iteratively, you will figure out that this should be 0 and phi 1 should be 2 in this example, right? In this example. But let's say that now we have changed this to this 2.2, maybe 5.9, something like that, 1 and 3 like that. Now this part is different. Now 2.1 comes here, then 4.2 comes here. Now probably this might not be 2, this might be 2.1, and this might be 0.1. We don't know. That's the process that we need to run. We need to run this one and we need to figure out these parameters. When you finish finding the best set of parameters, we call learning is done. After that, you don't need to learn. Learning is done. Now what? It's just a simple application of mathematics after that. Because if let's say that after doing all, you have learned the model is like this. So therefore, after that, what you have is 77.2 minus 74 times x. So every time you get this number and substitute here, you get output for any unknown input that you have used, which is not inside the training data set. So this is what happens inside the black box. Okay, please let me know. Is it clear up to this point? What I said, is it all good up to this point? Your feedback is so valuable here. Is it clear what I'm saying up to this point? You can send me a message through the chat.
Yes.
You don't need to, yeah. Even you can unmute and let me know feedback. Like I need some feedback to move forward so that this is reinforcement learning. That means I get your feedback and I'll take a different set of actions after that probably. Yeah. Okay, I'm getting several replies here. It says yes, so I assume that it's the same for others. So let's move forward, right? Okay. Now this is the model that we are trying to learn. Now, in civil engineering, there are a lot of machine learning related applications actually. So this I'm not sure whether you are using actually this name Abraham's law or different other name, but in literature I found this name. So it doesn't matter like what's the name of here. Probably it might be different, but this is a relationship where we looked at the water cement ratio and the compressive strength. Now this is the model. You can see that there are these brown colored dots are actually data points, and this red color line is the model that has been fitted to this data. So you can see that you can now initially what happens, you can start with any numbers like to a and b, any number. So when you use different values for a and b, you'll get different curves, right? Different curves. So when a and b is different, ultimately you figure out the best set of a and b so that the difference between the inputs and the predicted values are almost same. So that's the why. So if you change a and b, and you can figure out a and b in different ways, and you will find thousands or infinite number of curves, but there's one curve that reduces this gap a little. So that is the one. Okay, now what has happened here? We choose a model. Model means A and B. We define a good fit, and until you get the best outcome. So what is then in summary? What is this machine learning is all about? You train a model, and you need to have a loss function. Loss function means the difference between the predicted and actual one, and you try to optimize and fit the data. You try to get the best set of parameters and fit the curve. So modern machine learning changes the flexibility of step one and the step three. This this whole idea is pretty similar. Pretty similar. Okay, right. Now there are a set of things that when you read the books, when you try to read research papers, and when you try to learn, there are a set of terminologies that come across again and again. So therefore, it is good to keep some of these things in mind. Now, throughout this lecture, we use these symbols for these features. Like for input, we usually use the variable x. It is the feature vector, like in this example, cement, water, those kind of things. Then there's an output, like compressive strength, and those are the outputs that what we are trying to predict, output, target. Then the number of training samples, you need to have training samples in your data set. The total amount of data is I. Then the training set is training samples you have, training data set. There are those are xi and yi, those one particular set of data. Then you have the model, which is the mathematical equation that connects the input to the output. So then you have parameters, or these parameters, or you might have already heard the word weights. Weights of the machine learning model is the parameter phi that we try to find. Then the loss function is the one that we try to reduce when you find the phi. So we find phi so that loss is less, as much as less. So this we find the fitted parameters by using this optimization function. You try to reduce the loss function, and then we have another set of parameters. Now this is pretty important. Now there are a set of parameters that we try to figure out during the training process. That means by using the data, we are trying to find the parameters. Those are the phi values or the weights. Weights we find on the go during the training. But there are other set of parameters that are important, but we are not going to find them during the training. We need to figure out them before starting the training. So that those are the hyperparameters. So some hyperparameters are learning rate, number of layers in the neural network. Those are the things that you have to choose. So we'll discuss about this learning rate and the number of layers and those things later. But there are a set of parameters that you have to figure out by yourself, not the learning algorithm. So the parameters that we have to find so that we'll get a better model is the hyperparameters. Hyperparameters. So parameters are found by optimizer from the training data. Hyperparameters are set by the engineer before training and are tuned on validation set. Never on the test set. So that is something to remember, right? Now, probably you don't need to focus too much on maths here. This is how mathematically we represent this whole idea. So you have the x as the input data and y as the output data. Those are vectors. So you input to the system as vectors, get a vector as well. Okay, I'll try to skip some of the things for considering the time as well. So the usual training data set looks like this. Now you can see cement, water, fly ash, age. Those are the inputs. And your target, the output is the compressive strength here. So depending on the cement, water, fly ash and age, your compressive strength changes here. So our goal is finding a relationship for any unknown. For example, if I give you a combination of cement, water, fly ash, and age, you should be able to predict what is the compressive strength. So therefore, in this example, we have inputs, four inputs. So four inputs. So therefore, it's a dimension is four. So input dimension is four. You give four quantities as the input, you'll get one quantity as the output. So that the output dimension is one. Output dimension is four. So here, in this case, x, the input variable x would look like this. As an example, the first example would be 540, 162, 0, and 28. So this is a vector which is in 4 dimension. We write it like this, 4 dimensional space. So D is equal to 4. Output is one output, right? These units matter to us. Okay, so one thing is this important point. Another, when you practically try to train a model, these units, you have units for these quantities, but units are for us. In the machine learning model, for the model, it doesn't matter. For example, this the model, the 1 kilograms per meter square, and the column 5 is days. So these things matter to us, but for the learning model, it's not. So we need to know how to handle them as well, which we can learn. Right. If you summarize everything together, machine learning is all about these four things. Right. What are the four things? You have a model, a parametric model, mathematical equation, what which connects the inputs to the output. To get that, you need a loss function. You need to figure out a loss function. There are a set of usual loss functions that we can use. Other than that, we can derive a specific ones as well. Then we have the optimization to do to find the best set of parameters. Then we have to generalize it so that outside the training data set, it should work. So that's the generalization purpose. So you have linear regression, deep networks, k-means. Those are different methods that you can achieve this goal, right? We'll have a very brief look at supervised learning in general. We'll discuss this one and then we'll move to a different topic as well after that. Right. I said one thing earlier. At the very beginning, when you have a data set, if say that you have a data set on your hand, the first decision that you need to take is, by looking at the data, whether you go for supervised learning or unsupervised learning or reinforcement. That decision you have to take first. Now, let's assume that you have taken the decision to go for supervised learning, let's say. Now, when you go for supervised learning, all the problems that you are trying to solve, we can broadly categorize into 4 different categories. There are only 4 different categories that we have. We need to first take a decision which category it belongs, because in each category, the approach will be different. So you have a problem now, you are trying to solve it using supervised learning. That means you have a training data set with inputs and output pairs. Now we need to take a decision which technique that we are going to use. To decide that, this is for any problem, any problem that you are trying to solve can belong to one of these categories. How we take that decision? Depending on that decision, we have different problems, right? What we do is we look at the output of the data set. Output. Why? we take the look at we look at the output y of this data set. Now, depending on the properties of this output, it belongs to 4 categories. Number 1 is it might be a regression problem. What is a regression problem means? If your output is a continuous number, like let's say continuous number. For example, you try to figure out the price of a house based on certain things. It's a continuous number, single number. Or you try to predict some cost based on temperature, something like, let's say, those problems we call regression problems. Regression problems. So supervised learning, but now the problem at your hand is a regression. So how we identify whether it's a regression problem? But by looking at the output. If the output is a continuous number, it's a regression problem. Now, on the other hand, if the output is not only you need to predict more than one in output. Say that you are going to predict the let's say temperature. Let's say you are going to predict the weight and height both based on certain inputs. Now you have to predict two in outputs, not one. In that case, we call multivariate regression. So the same regression, because it's a continuous number that we are predicting, continuous number. Continuous numbers means these normal numbers like 1.2, 3.3, 4.5, 1, 2, 3, 10, 10.1. Those are continuous numbers. Those, if the quantity comes in that way, it's a continuous number. Now, there are two regression categories, regression and multivariate regression. So you need to figure out that. Third is binary classification. Sometimes your goal or the output is binary. That means yes or no, or it's true or false, or 0 or 1. Only two decisions. You, as an example, let's say that you input a picture to the machine learning model and ask whether it contains a tree or not. So answer should be yes or no. So it's a binary decision. You take one out of, you are not predicting a single number. You say yes or no type of answer, binary decision. These type of things we call binary classification. So you have two categories. You have to take one category as the output. So binary classification. The other is the output can be multiple. The output can have multiple categories, and you have to choose one of those. Say that you are inputting your input is a picture, and by looking at the picture, you need to say whether it contains a flower, tree, or a house. Now you have three categories. You have to divide. You have to, by looking at the picture, you have to now decide which category it belongs. Those type of problems we call multi-class classification. Multi-class classification. You have more than one class to classify. Any supervised learning problem that you take, your problem should belong to one of these four. There's nothing else that you can see, right? So either it is a regression problem, or a multivariate regression problem, or a binary classification problem, or multi-class classification problem. So after you take that decision that you are going to proceed with supervised learning, the next thing that you have to do is look at the problem and see, look at the output and see which method that I need to do, like whether it's a regression, multivariate regression, binary classification, no, multi-class classification. The methods that we follow is a kind of different, not fully different, but there are specific methods that we have to follow in these four categories. So, right. Now, if you look at the regression problem, it's one continuous number that you have to predict. So I'll skip some of the things because of the time constraint. So if I follow everything, I won't have enough time to cover data section. So therefore, I let you to read and understand some of the things. But look at this example here. This is a classical textbook example where you read those things. So your input is 6,000 square feet, 4 bedrooms, and earlier sold into 135K dollars in 2005, one parking slot. What you have to do is, by using these data, you have to predict the price of a house. Now, these are the model inputs. These are actual data. To our model, we just need to input the data. So we input the data and we get the output as 340. So it's a number. So it's a regression problem. You predict the house price. Another one is probably cement, water, fly ash, age, the example that we saw earlier. It's a regression problem. It's a regression problem. So you predict 52.1 based on these numbers. So it's a regression problem. Okay. Then multivariate regression, you'll see you can have multiple outputs. So your output now have more than one elements. For example, you will give a chemical structure of a molecular and you predict some parameters of that one, two parameters. So maybe another example is like this, which you can predict three outputs, like 41. Those are outputs. Right? These are the so it's very similar. Model shares the similar structure, and the output comes with. Right. Now, binary classification is you take a decision, yes or no, no type of decision. 0 or 1 is the output. How you do that is pretty straightforward. That means you do the very similar thing to regression, but now when you output that value, you pass it through a function called logistic function to convert the output to a probability value. So you check actually inside the model, what you do is you check the probability of whether it belongs to 0 or 1. So for example, if the probability of it belongs to 0 is 1.6 and probability of it belongs to 1 is 3.4, then you'll choose 0 as the class. So it's the probability. So it's a probabilistic method. So that means if the probability of y equals 1 given x is larger than certain threshold, usually the threshold is 0.5, then we pick that one. Then we pick that one. So how you do that is actually in the last stage, your output value, y value, passes through the sigmoid function to make it a probability. So I'm not going to talk about the details of maths behind this one, but it's up to you now, since you have a very large amount of resources, you can easily do that. So see how it actually happens in real world. Then multi-class means you have to get these probabilities for different classes. So you pick the class with the highest probability as the output. For example, here you can see that 0.86 is the probability of alligator cracking. That's the class. So other probabilities, you can see that 0.2, 0.02, 0.05. So those are not the highest probability. The highest probability comes for this one. So it picks that class as the class belongs to it. So this is done through what? Softmax. Softmax is the function that the network passes through that. Right. Okay. Now I'm not going to discuss about this fitting a model in detail because I'll skip that. But the motivation is that you need to reduce the gap between the model prediction and the actual output. So that's the task. So this is the predicted model predicted in this manner, y hat. Actual prediction is y. So this gap we'll try to reduce as much as possible. So I'll keep this outside because of this course, but you can see there's a worked example here as well. So you have the actual number and the predicted number, and then you can find this difference between those two and find the best set of parameters to do that. After calculating that set of parameters, you will find you'll have this kind of a table so that you can see how good our prediction is. For example, let's say that as an example, we'll see this one as an example. Say that your input is xi, your output is yi, and the model has predicted these values. So this actual value is this. Our model predicted value is this. Now the difference between those are like this. So you can see that here 48 is the actual value. What our model has predicted is 47.6. So that's a difference of 0.4. So here also you can see that there's a difference of 0.2, 0.8, 0.6. So those are the difference. Now we can, by looking at this one, we can see whether our model is how it is working. Right? Now, this sum of squared errors is one way of looking at. So you can see that these squared values, you take the squared values of these one, sum of squared values. Then the sum of squares total, SSTs. Now here, you have the actual value and the y bar is the mean, right? Y bar, you take the mean of these values, y bar. So this sum of squared total, that's nothing to do with the predicted value. So it's the mean. So that is 275 here. And the root mean square value. So you take this one, get the average and square root. So that is about this one. This R squared is a parameter, coefficient of determination, which is very commonly used in most of this machine learning work. So it says 1 minus SSE divided by SST. What it says actually, SSE means sum of squared errors, divide by the sum of square total. So what this R squared says. Now, if I give, let's say if you give me a data set and ask to do some prediction, probably without doing any learning, probably you might take the mean of all these things and you predict it as the mean. So this R squared R squared gives you how close, how good it is compared to just estimating the mean. How good it is. If it is closer to 1, it's good. If it is closer to 0, that means it is nothing. That's not no learning. It's just the mean that you have calculated. So that's what it finds. Now, even though you have these good things, let's say even though R squared is very good, it doesn't say that sometimes it might not very good. So now you need to read these numbers very critically. For example, in this R squared is 0.996, it's good, really good. But with I equals 4 points and 2 parameters, it means almost nothing. So because this number of data is very small, samples are very small, so therefore even though R squared is pretty good, we cannot take it as granted because it's very small number of data, the number of data. So we cannot have such predictions with very small number of data. Okay, so these parts I'll skip. This grade, how you optimize the parameters by using this gradient descent algorithm. I think when you are doing it in using Python, you have to pick optimizer. These optimizers are like Adam kind of optimizers. You pick these things we can discuss, but here it's not the time to do that. This learning rate is how fast you are trying to optimize these things. We'll keep it aside. And stochastic gradient descent is a technique that we'll use. So that's where these mini batches and epochs come, but we can keep it aside for the moment. Right? Generalization I'll discuss with the data, and this validation also I'll discuss it later. Right? So some of the metrics that you can use when doing regression is this absolute error, RMS, E, and R squared. So those are very common. And the other thing is these parameters also probably you have to give when you do after all doing training and everything. So you might need to calculate the accuracy, precision, recall, and F1 score. These have different names. So you can have a look at these aspects as well. So what it means by recall, what it means by precision, what it means by F1 score would be enough for this moment. Okay. Now, one other thing is that engineering judgment is pretty essential here. So model might predict a negative number. What should be a positive number also? So therefore, we cannot accept the data or the predictions as it is. So therefore, engineering judgment is pretty essential. Amidst the fatigue crack in the, so therefore, very, very important things are there. So the two errors are not equally costly. Now, it is with respect to the this diagram where we have true positives and false negatives and those kind of things. Now here, two errors are not equally cost. A missed fatigue crack in a steel grind may cost lives. False alarm cost one inspection. So therefore, you have to have this threshold in a certain level. So that's an engineering decision, not something related to learning. So therefore, engineering judgment is pretty essential in most of our work, right? Okay, now we'll very quickly look at these neural networks, right? Neural networks. We call that neural networks are the building blocks of this learning process, right? So here also, I'm not going to into the maths here, just for your information. When you are ready, you can read and try to understand. I have given the references also, but in this course, we cannot do that. But in a very simple shallow neural network means you have only one hidden layer. So this is what happens, right? This is the, now you can see this picture. That picture shows this equation in a graphical manner. So they are same, right? They are same. This is a graphical illustration of this equation. How you model in a neural network is this one. So phi naught times sigma phi j a of this theta function. Now you can see that there's a function a, right? This function. So what it means? You take the input and you multiply it by a weight. So this is the weight, and add certain number, another number, so it's kind of a bias, and pass it through this function and add again, get the summation here. And here also you'll add a bias. So that's the normal process. Now this activation function is very essential. Now this is pretty useful thing in learning. Now let's say that you have a data set like this. So your data are like this. So you need to predict the best curve for this data. Now you probably find this one as a straight line. But sometimes your data might not be like this. So your data might be like this. Now you cannot draw a single line. You cannot draw a single line. What you need is a curve or a piecewise linear curve. That means one line here, one line there, one line there, so that ultimately you get a estimation like this. Like this. These are called piecewise linear. These kind of things are called piecewise linear equations. Now, what we have done using this activation function is we have what we can in linear terms. You can combine many linear elements using activation function. This activation function, using activation function, you can break this line in certain manner. You can break the line in how we need and add them in a certain manner. So here, if you have time at home, please check on what happens in activation function. The most common activation function is ReLU. There are a lot of other activation functions which we can use. ReLU. ReLU function does what? It gets the, if you have a negative number, it makes sure that it is 0, otherwise it's the same value. So it is maximum of 0 or Z in this case. So therefore, if you have a curve like this, let's say, then after passing it through ReLU, what you get is this. All the other parts are 0. This is the curve. So that's what we have, right? Now, not going to explain this equation also in detail because of the time constraint, because you don't need to do these things if you're using a package to implement the algorithms, then these are already there, but it is good to have an understanding of what sort of activation function to use, what is this weighted sum, those kind of ideas. But this is not the time to explain those also. But in a regular machine learning class, we usually teach what happens inside each of these functional blocks, and we'll examine many examples and see what's going on. So this is an example for that one, but I'm not going to go into detail. So this is actually the shape of a deep neural network. Deep neural network means you must have more than two more than two hidden layers, two or more hidden layers. Hidden layers means these activation layers you need to have. So that's the only difference, right? So there are different activation functions. You can read by yourself probably. This is a back propagation is required, but not now, right? So that is about supervised learning. The simple summary is you will have a data set where you have input and the output on your hand, right? You will try to figure out a relationship, an equation where you can match those two together. Now, unsupervised learning is a little bit different to that. So you have a set of inputs on with no corresponding output. There's no output, you have data set. That's it. The absence of labels means there's no supervision. We cannot supervise, or we cannot teach the model how to learn. We cannot teach here because we don't have input and the expected output. We only have the inputs with us. So single right answer, there's no single right answer check. So the goal is not prediction, but a description. So in supervised learning, we can predict something. But in unsupervised learning, the goal is not prediction. It is we describe something. We find a pattern, a structure, or something like that. So usually in civil engineering, this is important as well. So there are a lot of cases where this can be applied. Now, what are the use cases of this? Cluster, group similar examples. Like we have group, we can group similar. So as an example, let's say that there's a store that sells, let's say, fruit. For some reason, let's say mangoes, and let's say what and let's say pears, apple, and those kind of things are mixed now. For some reason, during the transportation, something has happened. Now you need to separate them out. So that's the clustering, that you separate the similar groups, we separate together. Like you separate all the apples to one box, and then all the pears to one, and mangoes to one. So that's the clustering. So you have to sometimes need to do that. So with similar characteristic data, you have to group them together. Then sometimes this dimension reduction. So find few number of data to explain that one. So principal component analysis and those type of things. Then anomaly detection. You need to check the data and see whether there's an anomaly, whether there's something different to than usual pattern. So something like that. And most importantly, all this generative AI, Gen AI or generative, this GPT kind of things, generative algorithms, they come from this unsupervised learning background, from unsupervised technique. So generative AI belongs to this unsupervised. So the catch is this: with no labels, there's no test set accuracy. Validation of unsupervised result is a matter of engineering judgment, and you must supply. That means now you don't have a correct answer. So it's the judgment of our that says. So whether it has been clustered properly, you have to decide. Like whether there's an anomaly, we have to check. Whether generative algorithm now provides answers, like in ChatGPT when you write, so something generated. There's no label data set. It's all about finding the patterns. So someone has done this previously with this pattern. So when we ask the question also, some kind of pattern with higher probability comes out. So that's why all these ChatGPT and all the LLMs, they say that LLMs can go wrong because it's not one-to-one. So it's the probabilistic behavior. So therefore, engineering judgment is essential in this case as well. Right. This claiming clustering, I think, very important for civil engineering. Probably you might have already done that. I saw in the previous lecture slides, this was there. So therefore, probably you might have already understand. But it says that you find a middle point or center point, which is the closest to the center, and you cluster them. You group them together in certain manner. This is the algorithm that we can use. So then this principal component analysis is another area, this one. Then autoencoders are coming from this background. Autoencoders are end-to-end setup where you try to encode and decode in a certain manner. So these are pretty important in future for civil engineering applications as well. Generative models and latent variables are also coming from unsupervised learning background, which I'm not going to describe at this moment. Right. Now comes the reinforcement learning one. Here also, this reinforcement learning is the most mathematically heavy area in machine learning, and it is very kind of difficult to implement compared to other two. So these are called agents. Agents live in an environment. At each time time state, it observes a state, takes an action, and receives a reward. That's the basis. So you have an agent. Agent is the one who does something. It needs to take a decision. How it takes a decision? By perceiving the environment. So you have environment here, it observes the state of certain things. Like in this environment, there's certain state. You take a decision and you move to a different state. At the same time, you get a reward. So you will try to optimize the reward. You take the decision to optimize the record. That's how all our, let's say that in the company structure, it's kind of that. So you have a certain positions, you have to do something to promote through the structure. You take decisions with that end goal. So you have in mind where you need to go. You take a decisions to do that. So that's kind of a reinforcement learning. You take this course also for that part. For example, you might have something in your mind. So to achieve that goal, you have taken this decision to take this course. Now we can see if you learn, if you do all these examples, and if you do read through these ones, you'll get a better reward in future. So that's how it goes. So it's also reinforcement learning kind of idea. Okay, I'll skip these parts. Now this apart from this, especially fields like civil engineering, there's one other thing that we need to keep in mind. This is physics. Physics informed machine learning is very important, especially in civil engineering kind of, because civil engineering is almost like saturated area where you have very strong background understanding. So you have but many years of extensive work has done. So therefore, you have models which works with physical behavior. So therefore, we don't need to throw them away. We have to use them. For example, these different equations that you have in different applications you might have. So those information also we can plug into the learning model so that you can take better decisions. That means your model now needs to adhere to the physics behavior as well. So physics in the loss function, physics in the architecture, physics in the generator. That means you need, in addition to the data set, you give an additional equation also that you need to satisfy during the process. If you don't satisfy that physics equation, your model is probably wrong. So that's why. So these are called surrogate models. The best value use ML in civil engineering applications. So reliability, it might be more reliable than. Is that question? I think that's a. Is that question? I couldn't hear. Sorry, I couldn't hear. Is there a question or is it probably by accident? Seems probably by accident. Okay. Right. So this is the checklist that you have to follow. So you can read through that one and see how what are the things that you need to do as civil engineer who is using machine learning, what sort of things that you have to do before starting a project as well. So there are a set of ethics that we need to follow as well. these are like some of the models that we do. It's not fair and it's biased to different area. So we need to avoid them as much as possible, and we need to try to bring explainability to the context, because if you have a machine learning model without knowing what's happening, probably it might still do the job, but if we can have at least some explainability, that will be good. So those things are there. Then there are potential risks as well. You can discuss them and understand. Right. So we didn't go to maths part of the model, the machine learning, but we now have a kind of basic idea behind what's machine learning and what sort of applications that we do through machine learning and how to do that thing as well. Right. Now, this is the summary. We'll have a model. That's the equation that we try to find. Then we have a loss function where I try to minimize the loss function, and we need optimization for that, and we need to do generalization. We'll discuss about generalization in detail in the next lesson, right? The three paradigms are supervised and unsupervised and reinforcement learning. And five things to remember. So model is a curve fitting. Your split is your experiment, like bridge kind of thing. By bridge, by batch, by time, everything else is decoration. Then these metrics are important to look at. Physics is free information, like you have to give it to the model so that your model can generate them. And machine learning will not replace engineering judgment at all. So you need more engineering judgment because because now the model gives us answers. You need to check whether they are actually correct or wrong based on your engineering judgment. So those are pretty important things to us. And then these are some of the books that you can refer, but these are like mainly in mathematics, machine learning domain. So probably not in civil engineering directly, but you can, if you have time, you can read them. So that brings us to the conclusion of the first part of this lecture. So what we actually discussed is the pretty much essential stuff about the machine learning. Now, one thing that you need to remember or keep in your mind is this. When you are with a data set and when you are trying to start a project, you need to take a decision now based on your understanding of supervised, unsupervised, and reinforcement learning, which category that I'm going to go, whether I'm going to go with supervised, unsupervised, or reinforcement. Number one. Then, if you are coming to the supervised learning, then you have to take a decision whether it is a regression problem, a multivariate regression, binary classification, no, multivariate classification, and then move forward like that. Or else in unsupervised learning, whether you go for k-means or principal component analysis or generative method or whatever the method that you have to decide and move forward. In reinforcement learning, how you build the agent, what are the states, what are the actions that you have to decide by yourself. So those are the things that you have to do. So since you have packages which does this optimization of it itself, so therefore some of the stuff you don't need in mathematically, but you can use them and see how to get this one. So this is the overall background. The final word from this section is machine learning is all but finding this mathematical formulation. It's an equation. So when you have the inputs, you try to pass that input through a mathematical model equation to get the output. So therefore, there can be always errors. So that's why engineering judgment is essential. Engineering judgment is essential. So to get the engineering judgment, you need to have background knowledge. For someone like me, who is from outside from civil engineering, it is pretty difficult to do such things. So that's why the domain knowledge is important, because I don't know which variables might be positive, which variables might need to be negative. So therefore, if as a civil engineering person, that's a huge potential here to get into that domain, because you have already the domain knowledge. So that's the main point here. So there's a question in the chat. how to determine how many minimum number of samples needed to make a good fit model. It obviously samples mean good, but more samples mean need more time and cost. Right. It's asking about how many data samples to get a decision. That's a very good question. We are definitely going to answer that question in the next half of the lecture. So we can discuss it at that point. Okay, so we can have a break now. After the break, we can start discussing further. Probably we can pause the recording for the moment, and then we'll be back in 15 minutes in the second half. Second half will be more interesting, I guess, because it will talk about the data a lot. Right. Thank you so much, everyone. See you in 15 minutes. I guess after the break. Hope you all can hear me clearly again, and the screen is shared now. Right now, in the first half, what we tried was we tried to understand the domain as much as possible. Like we looked at what supervised, unsupervised, and reinforcement learning means. What we discussed is actually a very little information. There are vast information that you need to gather when you are trying to go in this direction, but you can do it by yourself once the initial set of ideas come into mind properly, so that you can work it by yourself. Right now we are coming now that what we discussed earlier was about the model, how we can have a model that can predict. When we try to build a model, we try to build a model that works as perfectly as possible so that we can get the best approximation. Now, to this model, what are the outputs? What are the inputs, and how this model will be built are all based on data. So therefore, if you don't have a proper data set, if you don't have a correct data set, what you predict might not be correct. So you need to build the model, but you need to build the model by using what? The data. So therefore, we need to talk about the data. Data is pretty important. So in usual machine learning, the preparation of data is about more than two-thirds of the work is on data. The other rest of the things are about the model. So therefore, you need to have a better data set. Now, therefore, we need to talk about data. So here we are starting with that discussion from this note. There are three parts here. We have three different kinds of things to discuss, and there are two different types of data that we are going to discuss as well: numerical and categorical data. And then we are going to look at some of the basic stuff related to them as well. Since we have roughly about little more than 1 hour, I don't know how much we can cover, but we can go a little faster. Probably I'll think if you are okay, I can take additional 15 minutes or so, so that we can go ahead as planned. Okay, we'll come to that stage closer to the finishing line. We'll start this discussion with numerical data. Okay, so we are trying to understand few things here. We are trying to understand what we mean by feature vectors and explore data sets, potential features visually and mathematically, and identify outliers, And we are going to understand 4 techniques that we can use to normalize the data, and uh, uh, what we mean by binning, and understand the characteristics of good continuous numerical features. Those are the things that we can discuss. Okay. It says that we can take additional 20 minutes after 4. Okay, thank you so much. And please send me a message through Zoom, so that I don't have a clock or anything around me. So therefore, you can send a reminder around 4, so that I can finish on time. Thank you so much. Right, we'll move forward. Now, this unit is actually sits with another 2 units that we need to discuss. So we are then, after this unit, we are going to discuss about categorical data and data sets and data generalization and overfitting also later. So what our objective in this unit is identifying numerical data. What are numerical data? So numerical data means integers or floating point values that behave like numbers. So behave like numbers. They are additive. You can count them, you can order them, and you can do mathematical operations. At the end of the mathematical operation, you get a meaningful something. For example, temperature, weight. Those are numerical values. Where, for example, when you add 2 temperatures, you get another temperature. So that is meaningful. As an example, some other numerical data. Let's say this postal code. Postal code, if you multiply a postal code by 2, what you get the result is not, there's no meaning of that. So therefore, those are not numerical values. So if you take a data set, there are a set of data that we can categorize as numerical data. There's another set of data that we can think of as not numerical data. These are categorical data. So for example, you can see that this is the postal code 4004. Now, if you divide it by 2, you get 2002. And if you multiply 2002 with 2, you'll get 4004. But there's no meaning of that. So those are not numerical values. So in your data set, once you have the data set, you need to identify what are actually numerical data, what are categorical data. So these are categorical data, which we can't do mathematical operations on those numbers. So we need to ask this question: does addition, ordering, or ratio of these values mean anything to the real world? For example, temperature. If you get the temperature and reduce 20, you get 10. It's a difference, so it has meaning. So therefore, it's a numerical value. For example, 12 years plus 5 years, 17 years. So there's a meaning for that one. It's meaningful. There's a meaning. So that's a numerical value. And if you get the probably subtraction between the 2 postal codes, there's no meaning. So those are categorical data. So there are 2 types of data that we come across in data sets. One, numerical data, the other one is the categorical data. So a column of digits is not automatically numerical data. So look at the meaning and not the time. So therefore, you must look at the data in that perspective. Right. Now we come to a very important discussion. Now we are trying to, now because we learned about the model earlier, now we are trying to understand what's the input to this model. So that's usually we have a data set. Data set means like, for example, if you look at the spreadsheet, like Excel sheet or something like that, you have entries in these things. Now, for example, here you have multiple rows and multiple columns. Probably these columns might have features of that input data set. And you have multiple examples. Now, in this example, you have 4 examples, 4 different data entries, like 1, 2, 3, 4. Those are there. Now, for example, let's suppose the data set has 5 columns, but only the B and D are features in the model. So there's a very big data set, but only we take this column and this column, B and D, as the inputs to the model. We don't use A, we don't use C, we don't use E. That's an engineering decision that we have taken earlier. And when processing this example in row 3, now when you input the row 3, that means you need to input 152 and 31 to the model. So that's the entries that we are going to input to the model. So that means In a large data set, we are not going to use all the features to the model. We don't need to do that. We have to use a meaningful set of entries. Now, when you input this data, which you selected from the original data set, we call that feature vector. A feature vector. Feature vector is an array of floating point numbers comprising one example. It sits between the data set and the model. Now, this is the data set. Probably, let's say this is an Excel sheet. From the Excel sheet, you create this vector we call feature vector. So it's a vector. Now, this vector should be a floating point vector. It should have floating point value. So this value has been now converted to a floating point number, 152.0 and 31.0. That's how we input. So we must input a floating point number to the model. So this is called feature vector. So this is the data set. In the data set, we have selected only a few columns as the inputs, as features. So therefore, whatever present in this feed as features will be input to the model as feature vector. Feature vector. So this is the first, third. When you input the third row, these are the values. This is the vector that we input to the model. Feature vector seldom use data sets row value. Even though we write it here like this, we usually don't input the original data value as it is to the model. We have to do something before that. We cannot usually input that there. These are the things that we have to do before inputting that data to the model. So you have the data set. You do something called feature engineering. You pre-process the data. You do something before inputting this data to the model. Those are called feature engineering. Some of these are normalizing, binning. Those are the different things we do. After that only, you do this feature engineering, you'll get a different value. So this is the feature vector process data. That process data is actually what we input to the model. So there are few steps that you need to do before inputting a data to the model. So you have a original data set in a spreadsheet, let's say. You process it, pre-process. We'll discuss about what we mean by pre-process. You process it further. Then after processing, you get a value. That value will be input to the model. It's not directly you take the data and input here. It's not. It's not usually the case. This is somewhat surprising, probably. Wouldn't a model produce better predictions by training from the actual value in the dataset rather than altered values? That's a fair question. But surprisingly, this answer is no. That means the result of why it is no, we'll discuss later in this course, right? So usually you have to do these things. Now, what is feature engineering? Feature engineering is the process of determining the best way to represent raw data as trainable values in the feature vector. So it is vital part of the machine learning. So what is feature engineering means? This is a pretty important thing, right? In any data set, you have the raw data set now. You are not going to input that raw data as it is to the model. You can't do that. If the process is what we do this feature engineering, which is the process of determining the best way to represent raw data. So we convert this original raw data to a format that best represented so that we can train the model. We can train the model in the feature vector. So this is very important part. There are two common feature engineering techniques that we use normally for numerical data. Number one is normalization. Second is binning. Normalization means converting these numerical values into a standard range. So we'll bring our all input data into a certain range. We discuss, for example, in between 0 and 1 or -1 to +1. That likewise we bring all the data into a standard range. Binning means converting numerical values into buckets of ranges. Like you might remember histogram, like you bring into a range. That means all the values in between 0 and 50 belongs to one bin. 50 to 100, one bin. Like that, you can use the bins or bracketing also another approach. We'll discuss further details into this process. Right. Now, before you create feature vectors, there are few things that you need to do. as engineer who is going to apply machine learning now, you need to do few things. Now, once you get the data as a spreadsheet or something, number one thing that most of the people do is you try to visualize your data. You try to visualize. That means some graphical method you can use. As an example, scatter plots, no histogram, something that you can visualize so that you can see patterns, anomalies, those things by yourself. So graphs help to find anomalies and patterns hiding in data. So therefore, please try, the number one step that you need to follow is try to visualize the data, try to see what's going on there so that you can see actual patterns. View graphs not only at the beginning of the pipeline, but throughout the data transformation. You can check it again and again during various phases of this process. Visualization let you continually check your assumptions as well. Second is statistically, you can evaluate the data. Gather basic statistics like mean, median, then standard deviation, percentile values like 50th, 75th, 25th percentiles. You can check them so that you can see, is everything all right? Are there any anomalies? All the patterns look okay, right? Because you have a certain judgment about the data. Now, by looking at this one, you can see some other things. So therefore, data visualization is pretty important. Don't over rely on basic statics as well. So anomalies can also hide in seemingly well balanced data. So therefore, that's why this engineering judgment is pretty important. Right. Now, why we do this visualization? Why we need to look at visually? Why we need to look at statistics is because of this. Because there can be outliers. Outliers. What are the outliers? An outlier is a value distant from the most other values in a feature or label. So they are like far apart from the other. Let's say all the other values are less than 10. There's one value which is about 1,000. So you can see that it is distant from other values. So it can be an outlier. Outlier often cause problems in model training. So finding them is important. You can see that we take decisions and we make the model based on the input-output relationship. If there are outliers, our model can go in a wrong direction towards the outliers. So that's the problem that we need to avoid. So therefore, outliers we need to avoid as much as possible. So outlier is a value distant from most of other values in the feature label. Now, a quick numerical test can do to figure out whether it's an outlier or not. When the delta between 0 and 25th, the difference between 0 and 25th percentiles differs significantly from the delta between 75th and 100th percentile, the dataset probably contains outliers. So you look at the 0th percentile, that's the minimum, and 25th percentile value and take the difference, that's the delta. And you look at the 75th value, percentile, and the 100th value. 100 means the maximum. So when you take those difference to see very high difference, then there's a chance that you have an outlier there. So for example, in this example, the 0 to 25 is a 4.75. The other 75 to 100 is 395.5. So this speech feature most certainly contains an outlier because of that. So that's a simple test that you can do. As an example, look at these numbers. So these are ordered set of data. N is equal to 20. So that means there are 20 data samples. They are ordered 3, 5, 6, 6, 7, like that, as you ordered. So if you look at 0th percentile here is 3. 0th percentile means the minimum number, that is 3. And 100th percentile is the maximum value, that is 412. And 25th percentile is, so here we have 20 data. So therefore, 21 divided by 4 is the 25th percentile. I think you know how to get that. 0.25, 25%. Times n plus 1. So n plus 1 is 21. So that is this one. So this is 5.25, right? 5.25. 5.25. 25. So 5.25 means 1, 2, 3, 4, 5. So this is in between 7 and 8. So how to get that? Then 7.5. So therefore 7 into 4 plus 8 times 3 into 4, that is the 75%. So what is this then? We have 24 plus 731 divided by 4, which is equal to 7.75. Yes. So this is the 25th percentile. 50th means the median. So that is a 10.5 in this case. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it is 23 divided by 2, it is 11.5, correct? And 75 also you can take in that manner. Right. Now, these are the percentiles that we have now. We have this one. Now, if you look at the difference between the delta between 0 and 20, it is 4.75. And if you take difference here, which is very large number. So very large number. So that means that's a mismatch. So usually they need to be very kind of similar numbers. So therefore, there's an outlier. Now we have to find the outlier. Now here we can see that this might be an outlier because all the other numbers are very small and this one is a very large number. So that's how we can figure out these outliers. Like this is just a test, right? So, and the other thing is this mean and median comparison. And mean is very high here. If you look at the mean by adding all these things, mean is a very high number compared to the median. A single huge value is dragging the mean up. That means so median is that is symmetric is the tail here. So those are the things that we can see to check whether there's an outlier or not. This is the test that we did. So those are the things that we can see there. So the compared to 0 to 25th percentile, you have like more than 80%, 80 times a large difference between 75 and 100 percentile. So that tells that there's something wrong. How go ask about the 4112 here, the 412. The statistics found it only domain knowledge decides whether it is actually typo or real measure. Now, by doing this statistical testing, we have figured out that there should be a problem here. But whether we are going to take that out or not, it's a decision of the engineer that has to take, because some of the outliers are not actually outliers. So outliers means it's distant from the other data, but probably it's a correct data as well. So therefore, when you found an outlier from the statistical testing, you have to take a decision whether to keep it or remove it. So due to a mistake, for example, extra zero typed somewhere or malfunction the instrumentation or something, so then you have to delete that entry. You have to generally delete the example containing that line. So because you can't proceed with that because it does an error. The other thing is sometimes even though it looks like an outlier, it might be a legitimate data point. It's not a mistake. So will the trained model need to infer good predictions on these outliers? We have to ask whether we have to keep it or not, right? So if you are going to keep these outliers in your training set, outliers in certain features, sometimes mirror outliers in the label, so they could actually help the model. Sometimes it is not. Sometimes you have to entirely delete the outliers or apply more invasive feature engineering such as clipping. We'll discuss about clipping. Now, there are two things that you have to do here. You find the outlier first using the statistical method. Now, outliers means it is distant from the existing other data. Now, then you have to take a decision whether to keep it or not. That's a judgment that you have to do. So probably it's a mistake or something that you figure out, then you have to remove it. Otherwise, if you are so sure that it's actually correct, then you can keep it and move with that. Okay. Now, since we discussed about normalization as a feature engineering mechanism, we have to see what is actually normalization means. Now, we have removed that outliers, right? Now we looked at these things and we removed the outliers, and now we have a data set with us. clean data set without with less number of outliers probably. We have a good data set. Now we need to input that data to the model. But before that, now we have to do this feature engineering. So one part is this normalization process. The goal of normalization is to transform features to be on the similar scale. As an example, in the original data set, your feature X might go from somewhere to here, like 154 to a large number like this. Feature Y might be very small in range, 5 to 22. So you can see that they are in two different scales. So feature X is ranging from very small number to very large number range. Feature Y is still small number range. It varies. Now, we don't usually like to have this kind of feature. Like you can see that feature X is ranging a very long span it has, but feature Y is less. So therefore, we'll try to bring it down to a common range. So here you can see that in the below picture, what we have done is we have brought this X into 0 and 1 range, Y also into 0 and 1 range. Why we need to do this is actually we are going to discuss later. Right, but this is the normalization means. So your range, you don't need to cap the range, but you'll bring it down to a standard specific region for all the features that you are going to use in the model. So what are the benefits by doing this normalization? So there are four main things. Model converge more quickly if you use normalization. Because when different features have different ranges, gradient descent can bounce and slow converge. Because you have a very large range, so you can understand that it takes a lot of time to converge. When you have a lot of a range to cover, it takes a lot of time. But in advanced optimizers can do that also, but it anyway takes time to do it. So this model infer better prediction. When different features have different ranges, the resulting model might make somewhat less useful predictions because like you have a very big range here. So different features have different ranges. So the resulting model might make somewhat less useful predictions because of this reason, because range is very large. The other thing is avoids to none, not a number thing. When a value in a model exceeds the floating point precision limit, the system sets it to not a number. Once one number becomes not a number, all the others in the model eventually becomes not a number. Because, for example, think that you have very big range. If you divide these things, something in a very large number, it is going to closer to 0. Now the precision is not enough because usually you use 32 floating point decimal places. Now, if it is not enough, then you are going into not a number range. So it is not good. But when you range it between 0 and 1, probably you can avoid those sort of things. And learn appropriate weights per feature. Without feature scaling, the model pays too much attention to features with wider ranges, not enough to features with narrow ranges. So automatically this happens. Now, for example, at the very beginning, the model gives more attention to the features with the high range, very large range. But later, when you train, sometimes you can come at after in iterations, you can come to a certain stage and you can train that, but it takes a lot of time. But initial stages, definitely more attention will be given to those. So you can avoid these things by using normalization. So if you normalize a feature during training, you must also normalize that feature when making predictions as well. Now, for example, these are, as an example, look at this, there's feature A, here feature A, it goes from minus 0.5 to 0.5, feature B goes from -5 to -5. Now here, both spans are relatively narrow, small narrow, but B span is 10 times wider than A. So it goes from 10, here it's 1, so 10 times wider. Therefore, at the start of training, the model assumes B is 10 times more important than A. taking a training takes longer than it should, and the resulting model is suboptimal as well because of this reason. So you think the model thinks that A is more important, B is more important than A because of this reason. So if we can bring it down to a range, common range like -5 to +5, that won't happen. And when you have a severe disparity, this case is even prominent because you can see that one feature is -1 to +1, the other one is very large. So therefore, we must, in these cases, we must do a normalize it. Otherwise, it is pretty difficult to get a proper answer. So your answers will be suboptimal and it will take a long time to converge. And entirely sometimes fail to converge as well. So therefore, those things we have to think. Now, the rule of thumb is this: normalized numerical features covering distinct different ranges. Also, normalize a single numerical feature covering a large range as well. So, if you have these different features that are different in ranges, you have to anyway do this normalization. If you have any questions, anything, please let me know. I hope they are clear enough. That's why I thought, but if there's anything unclear, please let me know. So these are the 4 techniques that we can use to do the normalization. There are 4 different ways that we normalize in machine learning context: linear scaling, z-score, log scaling, and clipping. Linear scaling means you take the value and minus the minimum value of the data set, and they take divide it by the difference between maximum and the minimum. Z-score means you take the x value, minus the mean divided by the standard deviation. Then log scaling means you take the logarithm, natural logarithm. Then clipping means you cap the values to a maximum and lower. So you don't allow your values to go beyond certain value, and you don't allow your data to fall down to a certain value as well. The choice is driven by the shape of the features distribution. So which normalization technique that you are going to use will be decided by the shape of the features distribution. So we'll see what are these things. So we'll start with linear scaling. Now you can see that these numbers I explained earlier usually range from 0 to 1 or -1 to 1. So as an example, if you have a range between 100 to 900, a particular example, let's say 300, then after normalizing, what you get is 0.25. So original range is 100 to 900, but now after normalizing, it goes from 0 to 1. And our sample, the current sample, lies at 0.25. So that's the linear scaling. Now, linear scaling is a good choice when 3 conditions are satisfied. What are they? The lower and the upper bounds of the data don't change much over time. The feature contains few or no outliers, and those outliers aren't extreme. The feature is approximately uniformly distributed across the range. And these are important points because now, by looking at the data set, you have to choose which normalization technique that you have to use, right? So these are important. The lower and upper bounds of the data don't change much over time. So if your lower and upper bounds change, that means your normalized values also change. So you don't need that to happen. So if your data change over time, the upper and lower bounds change a lot during the let's say with the time. So then linear scaling is not a good choice, right? You need this upper and lower bounds to be almost fixed during the entire process. So outliers you don't need to have, especially in the extreme. For example, think that maximum number is an outlier, then all the scaling is going to be wrong because you take that, right, the minimum value and difference between the maximum and the minimum. So if the maximum is outlier, we are in trouble. So also the features uniformly distributed across the range, it will be good. Hopefully like this. As an example, this kind of an example. Age. So age is between 0 to 100. So the distribution, the histogram, if you look at somewhat like this, you can see that in this area, it is kind of flat. So this is good. That's the uniform distribution in this area. So that kind of a vector feature, we can apply linear scaling, right? Okay, up to this point, is it clear what I'm saying about this data thing? Is it clear? You can send a message so that I'm going to be far faster. That's why I'm asking, like, is it okay or good up to this point? Okay, good. Yeah, it says yes. Right. Okay, I will move forward. So you can check whether you got the idea. For example, try to answer by yourself. Suppose your model has a feature named net worth that holds the net worth of different people. Would linear scaling be a good normalization technique for net worth? Why or why? Take a second and think. If we don't have much time, I'll quickly jump into the answer. That's no. Why is that? Because if you look at the graph like this, it is not roughly uniform anyway. So this feature contains many outliers can happen, and values are not uniformly distributed across the range. And most people will be squeezed into very narrow band of the overall range. Like most of the people will have less net worth, and very few will have higher net worth. So this is a like power kind of power law kind of distribution. So you have low, not an uniform distribution. So therefore, it is not going to work here, right? Then Z score, which you are familiar with most of the time. So Z score is the number of standard deviations a value is from the mean. So if you have a data set, the given data, how much standard deviations it is away from its mean. It's the Z score. That's what our A-levels exam also tells us, right? From the mean, where are you standing? How many standard deviations? Like if your value is 2, that means you are 2 standard deviations greater than the mean, right? Plus 2. If a value is 1.5 standard deviations less than the mean, has a Z score of minus 1.5. So this is how we calculate it. We get the value and we reduce the mean and divide by the standard deviation. So you can see this example. If you have the mu value and the standard deviation, then you can easily calculate. So Z score scaling means storing that feature's Z score in the feature vector. The shape of the distribution is unchanged. By doing Z score, shape of the original distribution won't change. It is a shift than a stretch. So subtracting mu centers data at 0, dividing by sigma gives it a standard deviation 1. So that is what we do here. So if your raw data looks like this in the blue color, your Z-score data also would exactly the same shape. But the difference is this axis, x-axis. So here it goes from 110 to 290. Now it goes from -3 to 3. So this is the mean lies. Identical shape by doing Z score. So if you look at this again, this is the raw data. Now Z score values are like this, -1 to 2 here, because this is now not symmetrical. So you can see that it is the same in Z score as well. So we need to read this axis very carefully, very carefully. So in the raw values, it goes from 0 to 29,000, while the Z score goes from -1 to 4.8, somewhere around that. Another big thing that we can look at is the normal distribution. Once you get the classic distribution, we can take we can count what's the percentage of values that are inside the standard deviation range. For example, here, -1 to +1, -2 to +2, -3 to +3, -4 to +4. So what are them? So you can see that 68, 95, 99, 99.99. So that means in between standard deviation -4 to +4, almost all, like 99.9 is there. So can we say that if the z-score value is larger than 4 is an outlier? So data points out is out as an outlier. Since outlier is a concept without strict definition, no one can say it sure because of that. So you need to do it, you need to analyze it further to get such a decision. So that's the main idea here. So suppose your model trains on a feature named height that holds the adult heights of 10 million. Would z-score scaling be a good choice for this one? You can again think whether it is a good or bad. In this case, yes, because z-score scaling would be a good normalization for height because this feature confirms to a normal distribution. So usually heights are in normal distribution, so this is okay. Right. Log scaling means this. You take the natural logarithm and pass it, right? Like this one. So if the original data is 54 point something, you get roughly about 4.0. So log scaling is helpful when the data conforms to a power law distribution. So power law distribution means something like this. Now distribution looks like this. For low values, you have a higher output. For larger values, you get a lower value. So that is why here low values of x, you will get the high values of y. And as values x increases, you get a quick decrease. And consequently, you'll have for very large y, you have very low y values like this. So this kind of a shape is the distribution. So if that is the distribution, this log scaling will work. You can easily see why it is so as well. Now here, look at what happens in the model. If you input this one, almost all the data entries are here, right? But when you take local, it starts to get distributed. So you can see actually they are distributed. That's good for learning and training process. So scaling changes the distribution, which helps train model that will make better predictions in this case. Because otherwise, almost all the data entries are here. Like everything is here, but nothing is like very real here. So it is now distributed. So therefore, you can scale it out. When you take local, you know that small values you kind of get distributed. So that is good. And it has much opportunity to train in that manner. Yeah. Now, the other thing is clipping. Clipping is a technique to minimize the influence of extreme outliers. So if you have any extreme outliers, you can clip them and out. In brief, clipping usually caps the value of the outliers to a specific maximum. So you don't allow your training data set's maximum value pass beyond a certain value. As an example here, the rooms per person feature. Let's say total numbers divided by the number of occupants. So 99% of feature value conform to a normal distribution, roughly 1.8 with standard deviation of 0.5, like this kind of a distribution. So this is a normal distribution up to this. But you can see that there are other values, very long tails, very long tail. So you can see here. So up to about 70, you have different values here in this distribution. Now, what you can do is this. Instead of going for that one, you can cut here. So you won't allow these to go. So if some number is larger than 4, you will keep it 4. So these all are clipped after 4. So you don't care about the other values. So in the data, that's another way of normalizing, right? So what actually clipping means is clipping the feature value at 4.0 does not mean that your model ignores all values greater than 4.0. Rather, it means that all values that were greater than 4.0 now becomes 4.0. So you don't remove the entry. What you do is all the values beyond 4.0, now you have clipped at 4.0. That is the clipping. So you have to use one of these four methods when you normalize the data. Right. So these are the summary of the four normalization techniques: linear, z-score, log, clipping. You have to see when to use when you have a uniform kind of distribution. Linear is better. So when you have a normal kind of distribution, the bell shape, then z-score. When you have a heavy tail, like this power law distribution, then you have log scaling. When you have contain extreme outliers, clipping would work. So these are the decisions that you have to take when you train a model, right? These are a picture. Now you have the this is the flat kind of linear scaling works, bell shape, z-score, heavy tail like this, log scaling works you can use in the model. So what you do is this: plot the histogram, recognize the shape, then pick the matching technique, clip if extreme outliers are there, replot and see. Again, if you find outliers, you have to do that. Like you continue until you get satisfied with the data set. That is the process that you have to follow. Now think about this, which technique, this is an exercise, you can think of the answer on the code itself. Which technique would be most suitable for normalizing a feature with the following distribution? You can see that it's kind of a normal distribution. So therefore, a z-score would do it better. There's another example. You are developing a model that predicts a data center's productivity based on temperature measure. Inside the data center, almost all temperature values fall between 50 and 30. Once or twice per year, extreme hot days, a few values between 31 and 45. So which would be reasonable normalization technique for this one? Definitely something clipping would work here because you need to clip some of the values. And think of these questions. Right. Now we discussed about two things that we can do for feature engineering. One is normalizing, the other one is binning or bracketing. Now the bracketing is a feature engineering technique that groups different numerical range sub-ranges into bins or buckets. In many cases, binning turns numerical data into categorical data. So you have bins. As an example, see this. Now you have data from 15 to 425. So bin 1 is 15 to 30. Bin 2 is 35 to 170. Likewise, you can have 5 bins. Now, every time a sample comes into one of these bins, you will put that value into that bin. For example, if you have a number 40, that belongs to bin number 2. If you have 120, it belongs to bin 3. Likewise, you can the binning. So bin 1 spans from 15 to 34. So every value with x between 15 and 35 ends up at bin 1. So that is the binning. So it is what actually we do in histogram also. But this is very important technique in machine learning, right? And there's something to learn also here. How you use bins in feature vectors. Now, this is the feature, because feature vector means you have to input a vector, like a numerical value to the model. Now here, look at what we have done, because we cannot enter range into the model. We have to input the number, how we create this number. Now here we have 5 bins. So therefore, we have used a vector of 5 variables. Since this is 1, the feature vector is 1, all the other entries are 0. Bin 2 means second element of the vector is 1, all the other elements are 0. Third means Third one is 1, all the others are 0. Fourth one is 1 here, all the others are 0. Similarly, fifth. So when you come in your data, when you come across a point that belongs to bin 3, for example, 152, bin 3, what you input to the machine learning model is 0, 0, 1, 0, 1. So that's the you are not inputting 152. Instead of that, you input this vector to the model. So model will be trained on this one. So even though X is a single column in the data set, binning causes a model to treat X as 5 separate features in this example. Therefore, the model learns separate weights for each bin. Right? So therefore, the model will learn a separate weight or parameter for each bin. So each bin will be separately considered in this case. So instead of one weight, W forcing a single linear trend across X, the model gets W1 to W5, one per subrange, each free to point where the data stays. So this is pretty important thing when you actually implement the models. Binning is a good alternative to scaling or clipping when either of the following is met. The overall linear relationship between the feature and the label is weak, and feature values are clustered. Sometimes they are useful, right? Sometimes we need to consider only ranges. On those types, we can use them. So linear relationship, if you have a linear relationship that we can use, then scale it. Otherwise, we can use this binning. So these are the things, right? I'll skip this part because of the time. The number of bins also we need to take carefully, because if you have very large number of bins, it's also a bad idea, because then your training and everything is there. So how many bins that you're going to use, it's again an engineering decision that you have to check. Okay. There's another technique which we call quantile bracketing. That means you try to create the brackets which are roughly equal number of examples, like quantile. So that creates bracketing boundaries such that the number of examples in each bracket is exactly or nearly equal. But that is somewhat, it's kind of not perfect. It can go wrong as well, and these boundaries in that manner. So it is a technique that is there, but somewhat less popular. Okay, this scrubbing is another thing that we can do. Is this as an example? This if you take an analogy here, apple trees produce a mixture of great fruits and wormy misses. Yet the apples in the high-end grocery stores display 100% perfect fruits. So between orchard and grocery, one spends significant time removing the bad apples or spraying a little wax on the required ones. As ML engineer, you will spend enormous amount of your time tossing out bad examples and cleaning them before you input them to the model. So even a few bad apples can spoil the large data set. So therefore, cleaning process, this pre-processing will take a lot of time, and it requires a lot of amount of time as well. So there can be these are the problems, usual problems that you can come across in a data set. What are them? So omitted values. A census taker fails to record the resident's age. Some of the values are omitted. Then duplicate examples. A server uploads the same logic twice. Out of range feature values. A human accidentally type an extra digit. A bad label. Human evaluator mislabels a picture of an oak tree as a maple tree. Likewise, there can be these other common reasons that you can have data. So many examples in the data set are unreliable due to one or more of these problems. So you can do two different ways to cleaning up these things. Sometimes some of the things you can automate. You can do it through a script. You can write a script, a program to omit some of the values, duplicate examples you can remove, out of range features you can fine tune the script. That means you can do part of cleaning through script, automate. Like you can hand over that to the computer. But some you cannot remove in that manner. So bad labels need a different tool. When labels are generated by multiple people, statistically determine whether each rater generated equal sets of label. Because people take a decision when you manually, if you when you have input a label, so each person views it as different. So perhaps one rater was a harsh grader than the other and use a different set of grading criteria. So those things we have to manually do it. So therefore, you would typically fix examples like contain bad features or bad labels by removing them entirely or inputting their values. So you have to do something. This is very careful, need to do very careful. So what are the qualities of good data set? So it's clearly named. Each feature should have a clear, sensible name any human can understand in the project. For example, house age, like this, it's not recommended. House age, years, something like that. So that anyone who is working in this project can understand. These things are not a problem for the model because this is a thing for the project management because you need to continue the project. So anyone comes new to do the project should also understand it. Check or test before training. So these things, yeah, user age in years. It's wrong now here. There's a typo. User age in years is 24. So those things you have to take careful. One other thing is we use this magic value sometimes. A magic value is a purposeful discontinuity in an otherwise continuous feature. For example, think that suppose a continuous feature like watch time in seconds can hold any floating point value between 0 and 30, but represents the absence of a measurement with the magic value of -1. This is not recommended. That what I mean is this. Now you have a data set which spans from between 0 and 30. And sometimes in some entry you don't have, like let's say 0, 1, 4, 5, 8, 10, like that. Then now some of the entries are missing. Some of the entries are missing. Now for the missing entries, what you have done is you have entered -1. Now this is wrong. Why? Our original range is now here the magic value is -1 that we have used. We have purposefully put that. But the range is between 0 and 30. So it is not a good thing to input -1 here. So the recommended method is this. So you can have a separate Boolean feature to indicate whether it's supplied, whether that data is there or missing. So watch time in seconds is the value. So is the watch time in seconds defined? True. So watch time in seconds 0. So instead of -1, we have assigned 0, but it is not defined. So it is a missing data. So we tell the model that this data is missing also. So this works, the continuous feature now only ever hold a real in range deviations. So that's good. This Boolean thing is doing that one. So same idea. Yeah. Okay, this part I will skip today because of the time. But one thing you should know, you can read the other parts also to understand it better. One thing is that please see what are the things that you have to do if your data set contains numerical values. So before that, you need to do something before input the data to the model. So therefore, carefully need to do that, right? These things you can revisit again, and this is the conclusion. So you have the raw data set, you have to do something, and before input it to the one, you can go to this reference and try this course like that. It's from Google, and you can actually, these are source materials. This kind of slides are from this course. So therefore, slides were prepared using this course. So therefore, these concepts you can apply in this course and see. Actually, you can test your understanding further. And please try this at home. So don't just read through this one, just try that and finish that part as well. So then you can see actually how you can work with the numerical data through this course, right? Okay, we'll then move to the other topic. I don't know, probably the last part I might not be able to finish, but we'll discuss about this categorical data part. Then we can see whether we can go to the other part also. Roughly about the any questions, please let me know through this one. So then the other part is this categorical data. Categorical data. What we have is numerical and categorical data. We need to treat them separately. So categorical data has specific set of possible values. The different, for example, different species of animal in a national park, those type of things. So these are numbers, but you cannot do these mathematical operations, right? So the numerical values, we know how to treat them. Now the categorical data, right? Now in the categorical data, you have to do something called encode. Encoding means converting categorical data to numerical vectors that the model can train. So the model can train on only on numerical values. So you need floating point number. So therefore, you cannot input categorical data as it is. So therefore, you need to pass through a process called encoding. Encoding. As an example, let's say your actual input that you need to pass is dog, maple, these kind of things. But you pass it through an encoder so that you convert it to a number. Somehow you convert it to a number. So this number now you can feed into the model. Without that, you cannot feed it. So why this conversion is necessary? It's not an optional thing. It's a must. You must do it. Models can only train on floating point values. Models can't train on strings such as dog, maple, those things. So this is not a matter of convergence or performance. It's a hard constraint on what the arithmetic inside the model can consume. So encoding is a must, right? Now let's see how we can do this encoding, right? So now our purpose now is to find a way to encode, convert the categorical data into numerical data. How we can do that? But to do that, we need to understand a few other things. The first is this dimension. The term dimension is a synonym for the number of elements in the feature vector. Number of elements in the feature vector. As example, look at this one. The feature, snow today. It's a feature. So now there are two categories, true or false. Right? The skill level, beginner, practitioner, expert, three categories. Season, 4, winter, spring, summer, autumn. Likewise, it's the number of days, day of the week, 7. So you have this type of features. So feature name and the sample categories are these. Now, when a categorical feature has low number of possible categories, you can encode it as a vocabulary. With the vocabulary encoding, the model spreads each possible category value as a separate feature. During training, the model learns different weights for each category. Let's see how we can do that. So probably you might not understand this, what it means now, but through an example, we can understand it. That is important because otherwise we cannot input the categorical data to the model. Suppose you are creating a model to predict a car price based in part on a categorical feature, car color. Let's say red cars are worth more than green cars, as an example. Since manufacturers often offer a limited number of exterior colors, car color is a low dimensional categorical feature. So this categorical feature is colors can be limited, like red, orange, blue, yellow, green, black, purple, brown. Those are the colors now in this example. Now, how we can input this data, whether it is red, green, blue, how we input that. So the feature is that whether it is red, whether it is orange, whether it is blue, yellow, that those are the things that we have to input to the data. How we can do that? Now, machine learning models can only manipulate floating point numbers. Therefore, you must convert this string to a unique, convert each string to a unique index number, right? How to do that? It's like this. What we do is this. This is called one-hot encode. One-hot encode. This is building a vocabulary is to convert each index number to its one-hot encode. One-hot encoding is what? Each category is represented by a vector of n elements, where n is the number of categories. If car color has 8 possible categories, the one-hot vector has 8 elements. So now this is the case. When you need to input the color red, what you input is this vector. First vector 1, then followed by 7 zeros. Then orange 0, 1, then all other zeros. Likewise, that's the number that you input. So let's say that your input is a red car to the model. So all the others are zero. This is the number this is called one-hot encode. So if it is a brown car, then 0, 0, all the zeros, and the last element is 1. So this is how you input the value. This is how we input the value. So this is the encoding process, one-hot encoding, which is very popular. So if you have a small number of dimension for the feature, then you can use one-hot encode. One-hot encode. I hope it is clear. For example, in your model, if your one input is color of the car, then when your example is red, you instead of red, what you represent it using this vector. Okay? That's the vector that you input. So it will be then trained accordingly in the model. It is the one-hot vector, not the string, not the index number, that gets passed to the feature vector. The model learns separate weight for each element of this vector. This one-hot method is pretty important. As an example here, let's say yellow, orange, blue, those are the inputs now. So you stored here, and yellow, this is the third one, second one, third one, it starts with 0, so 0, 1, 2, second point is 1 here. That's the input to the model. That's the input to the model. Okay. So this is a sparse representation. So you can, in the memory, when you store this one, you can use sparse relationship because you have so many zeros. So that's a feature with sparse. It's a sparse vector, right? So there are sometimes so many other colors also that are kind like outliers. So like numerical data, categorical data also contains outliers. Suppose that car color contains not only the popular colors, but also some rarely used outlier colors. Let's say all these outlier colors you can brought into one feature as well. So you don't need to care about others. You only care about these 5, and others you can combine and treat separate. Right. This high, when you have low dimension, this one-hot encoding is very good. Right. Encoding high dimensional categorical features needs to read. So when the number of categories is high, the one-hot encoding is usually a bad choice, because as an example, a one-hot encoder for last names in German would be 850,000 elements wide, of which exactly it's a very, very large vector. So therefore, embeddings are usually better in this case. Embeddings substantially reduce the number of dimensions, which benefits models in 2 important ways: trains faster and low latency, therefore, and infers predictions more quickly as well. So this hashing, also called the hashing trick, is a less common way to reduce the number of dimensions. This is a trick that we can use. So you have a hash function. Through the hash function, you get some number, and there's an algorithm. So the hashing maps a category to a small integer, the number of the bracket bucket that will hold that category. So I'll skip at this moment because of the time, so you can read and understand what happens here. So you can do these questions also later. Right. This feature crosses also, I'll skip at this moment because it will again drag us to a separate discussion. But you can read it. It's a very, very clear, and it's uh, easy to understand. So you can read and understand by yourself. Now, here what we discuss in these two topics is numerical and categorical data. What you need to do before you input those data into the model. Those are pretty important things. Actually, those are the things that you must do. Whatever the model that you use, you have to do those things. So therefore, these are really valuable. And this is a summary of the topic what we did. Similarly, you can go to this course and do these things by yourself. There are hands-on examples, so please do them and try to strengthen your understanding in those as well. Right. If you go to this final part, I think I won't be able to finish it, but at least some details that I can provide because there are very important concepts we can discuss here. The generalization, overfitting, underfitting, those kind of details. Probably you might have discussed some of these things already. But these are the questions that we can ask before starting this section. If you have had to prioritize improving one of the following areas in your machine learning project, which should have improve the quality of your data set, apply a more clever loss function or trick, which you need to do. Probably you might think that you need to do it something to the data training method or loss function or something, but it is not true. It is about improving the data. Data is everything about everything. Like in machine learning, data is the key thing. So therefore, you need to have a better data set. So in your machine learning project, how much time you typically spend on data preparing and transformation? More than half or less than half? Usually, you spend 80% of time on a machine learning project on constructing data sets and transforming data. So it's a huge amount. You can see that only 20% on training, hyperparameter tuning, those kind of things. It's all about data. If you don't have a proper data set, what you do after that doesn't have a value. It doesn't matter because wrong data provide wrong predictions always. So these parts we discussed, like you have CSOs, this Excel file, you have data, then you need to bring them. So one thing is that quality of data, how you can say that this data is good or bad. Your model should train on at least an order of magnitude of two or more examples than trainable parameters, right? You need to have a set of good examples. Now, if you have a very small number of data, then you cannot train a proper model because you are trying to identify a pattern on average. If you need to average a pattern or something rule, then you need to have sufficient data at your hand. Otherwise, you cannot do it. So that's one thing to remember. So model trains on large data sets with few features generally outperform model trained on small data sets with lot of features. So this is a very important point actually. As a practical person who is going to implement something, models trained on large data sets with few features generally outperforms the models trained on small data set with lot of features. So that you can see that data is the key thing here. So then there's no universal number that we can select a few dozens or trillions. It doesn't matter, but it should be sufficient enough to average the features. That's the key thing. Now, what do you mean by quality here? A high quality data set helps your model accomplish the goal that you need to achieve. Low quality data set inhibits that your model from accomplishing that goal. You cannot achieve that goal. So that is the quality. So there's no direct answer that if you can achieve your goal through the data set, that's a good enough data set for you. But if you cannot achieve that, that means it's a low quality data set. Then the reliability. What is reliability? Reliability refers to the degree to which you can trust the data. A model trained on reliable data is more likely to yield useful predictions than one trained on unreliable data. So these are few things that you need to think about the data set. So how we can get an unreliable data set is like this. Some omitted values can be there. So some entries have not filled. Then duplicate examples, bad features, bad labels, bad sections data. Those are the reasons for us to have a unreliable data set. So you can use automation as we discussed earlier. You can have a script to remove some things, but some you have to manually investigate and find. So this is an example where a missing data. So your complete a complete data entry would like this, but incomplete data entry would like this. So these are missing data. So don't train a model on incomplete example. Instead, fix or eliminate it. So you don't input this data entry as it is. You have to fix or eliminate. You have to either remove or eliminate. So you can delete the entire example and remove it, or else you can input a value. Like you can yeah, give another value, impute missing values. So convert the incomplete example to a complete example by providing well-reasoned guess. You can give an like estimated value and proceed those. When to delete, when to estimate it. Now consider deleting when the data set contains enough complete example. If you think that your data set has enough data, you can remove it. No problem, you just remove it. Only then that's okay because you have a large data entry, so this won't do anything. But when you don't have enough data entries, you cannot simply delete it because when you delete that, all the other features also go. So therefore, you can try to estimate it. Now, if you can't delete, don't argue, you measure. Right? Build two data sets. Now, you can if you cannot take a decision to delete, you can do this test. What is that test? That means you build two data sets, one with that entry, missing entry, the other one is deleted. You can delete the entire row and see. You will train the model and see how they are performing. They are performing almost equally, that means you can delete it. Then you delete it and move forward. Let's just test, right? So these are a few things that you can read and understand, I guess. So therefore, I'll move forward, can do this test. And these labels are important. So there are direct labels versus proxy labels. Sometimes you can have direct labels, like labels identical to prediction your model. So for example, if your model predict whether you are a bicycle owner or not based on certain things, you can have in your data set, you can have a direct label or the column saying whether you are a bicycle owner or not, right? A label identical to the prediction your model is trying to make. That is the prediction of exactly whether exactly that label is there in the data set. But proxy label is not. It is not that. For example, you need to actually decide whether you are a bicycle owner or not. But in your data set, there's no such column. What you have is a similar but not identical column. As a subscribes to bicycle related magazine or something like that, right? Direct labels are generally better than proxy labels. If the dataset provides possible direct labels, you should probably use it. Oftentimes, direct labels aren't available. So you have a data set. Your goal is to find whether someone is a bicycle owner or not. But in your data set, you don't have such a column. Like you are doing this supervised learning, you need to have that. But it is not. Instead of you have subscribe to bicycle related magazine. So that's a proxy label. That's what I'm saying, right? Proxy labels are always a compromise, an imperfect approximation of a direct label. So how some proxy labels are close enough to approximate, well, to be useful. So models that use proxy labels are only useful as the connection between the proxy label and the prediction is there. So for example, if you're using proxy label, there should be a connection between what you are going to predict and the proxy label, right? Otherwise, you cannot make that prediction, right? So you can try this question actually. Your company has this, so you need to predict which people own a bicycle. So unfortunately, data set doesn't contain a column named bike owner. However, it does contain a column named recently bought a bicycle. So would this recently bought a bicycle be a good proxy label or a poor proxy label? Actually, it will be a good proxy label in this case. You can read the answer as well, right? So you can generate data by human, you can automate the data as well through software. And this one, there are advantages and disadvantages, which you can have a look as well. Right. This part I'll skip at this moment. There are a few things that we need to divide the original data set. So this is an important thing. I'll finish with this one probably because of the time, but this is pretty important, right? When you have a data set, like let's say now you have a clean data set with you, you need to divide that data set before start the training process into actually three things, but here let's start with two: training set and the test set. Good software engineering project devotes considerable energy to testing. Similarly, we strongly recommend testing your machine learning to determine the correctness of the prediction. So you test it. So training set is the one that you use to model train, like learning process. You learn them. Testing is for the evaluation of the trained model. So you have finished the training. Now you need to check how good my machine learning model is in a separate data set that we have not used for training. You cannot use actually the test data for train. You cannot use your training data for testing purpose because training data has already been seen by the model, so it can do the predictions pretty easily. So therefore, there should be two separate data sets like this. Now, in addition, you usually needs to actually divide this whole thing into three sections. This is the best way of doing it. Training set is 70, validation 50, test 50. That's the normal rule, right? You can change it slightly here and there, but usually training is 70, validation is 15, testing is 50. That's how you divide it. Now, training set you use for training the actual model, and the testing data set is used to test the trained model. Validation test performs the initial testing on the model as it being trained. That means you tune your hyperparameters. You change the model, you change the number of layers of the model. Those things you do in the validation phase. So that means you train a model, you find out, you check the model accuracy, and you find it is not good. So you think you need to change the model. How you do that test? Using the validation dataset. On the validation dataset, you do this testing. So after doing this, like as a repetitive thing, in the validation set and training, you train, you validate, you train, validate. After that only you do the testing. After doing all the changes, you do the testing. So this is the process. Train model on training data set, evaluate the model on the validation set, then tweak the model, or you do whatever the changes that you need to do the model to get a better one, and iterate 1 to 3 times, and after confirm, you test it. If the test results are good, you are good to keep that model, or else you again need to change, right? That's how the things are moving. This is very important process, something that we all need to keep in mind. Right. The other thing is when to stop, until what we need to train, until where to stop. Those also are important things that we have to discuss. So please read this note at home. That's pretty important. Right. Probably this generalization means this. Now, the idea of generalization is pretty important. Your model should perform better in an unknown data set. Like you have trained on a data set, training data set, but when you apply that model to unknown data set, separate data set, that should perform better. If you cannot perform better, that means your model has not been generalized still. So this generalization is very important. Why it is not generalized? Sometimes it can be overfitted to your training data. So overfitting is the concept that we need to understand because of that. Overfitting means creating a model that matches the training set so closely so that it fails to make correct predictions on new data. Overfit. Your model is overfit. It is not a general thing. It's a very specific scenario because it has remembered the pattern of the training data set. So now it cannot move outside. It is only working when such pattern is there. An overfitted model is analogous to an invention that performs well in the lab but worthless in the real world. Now look at this figure. Now you have in this figure, you have blue marks for the locations of healthy trees and orange for the sick. So you need to now differentiate, cluster them. You need to sick trees and the good ones. Now look at what has happened in your model. You have identified the boundaries as this. So this model is an overfit. That means it's not generalized. So for example, if we ask you to do it, probably you might not do like that, right? Probably you might think that maybe somewhere like this would be okay, like something like that. But if you have overfitting, like this, now when you provide test data, you can see that it has failed because test data it is failed because of that. The complex shapes categorizes all but two of the training trees. If you think that shapes as model, this is a fantastic model, but you cannot do it in real world because this model has overfitted to the training data. So we don't need that to happen. Usually, there are two things. The model can be overfit. That means it's too tight to the training data, or underfit. The model has not identified any relationship in the training data. So you don't need that to be underfit or overfit. Model should fit to the data in general. That's what you need. So that is the main difference between optimization theory and machine learning. In optimization, you find the exact optimum. You try to find the best place. But in machine learning, you try to be good on average. So generalization is pretty important thing here. Right? So you can see here training data loss and validation loss. Now you can see here one way to identify whether your model has been overfitted is this. You look at these two curves. You get the training loss and validation loss. Training loss has gone down completely like this, and validation loss come here and goes up. That means this is overfitted. Overfitted. So the loss curve plots models loss against number of training iterations. A graph shows two or more loss curves is called generalization curve. The two loss curves behave similarly at the first, then diverge. That is, after a certain number of iterations, loss declines or holds steady, but increases the validation. So this happens because model now validation loss. So for unseen data, it's more errors come here. So after this point, it starts to overfitting. That's why it is the case. So usually these two plots should go in a similar direction. So you can read these few things at home to get further insights into this topic. So model complexity, like if you have a very complex model, this can happen. So a simple model generalizes better than complex model on new data. So that's why we don't need two complex models as well. If you have very complex model, that's a problem. So you need to find the best model as well. So that's a pretty difficult task at some point. Right? How you achieve this overfitting thing is actually by using this regularization, which I'm not going to discuss because of the time. But please read this part as well. And this L2 regularization, those things you have to use when the actual implementation. So these things, please read through at home and try to understand. So we discussed about these things in here. So please try this hands-on course as well, so that you will get a better understanding, right? Okay, so now I think our time is up. So we have to finish now. If there are, I went little fast. I'm sorry about that. I went fast because I need to cover certain things, but I believe that you get the fundamental insights that you need. So we discussed two parts: inside the model and before the model. So before the model is playing a huge role now, you can see. So therefore, please read through them, and after that you have the model. So by reading through these materials, by reviewing these things again and again, you get a better understanding of all these things. So if you have any questions or any doubts, just post in the WhatsApp chat. Probably even after 2-3 weeks, 2 months time, when you review it again, it doesn't matter, just post it there, so under my name, so that you can I can reply to you also. But I hope that during this period, the 3 hour duration, we looked at several fundamental things. I believe those things will be useful in your future journey. So thank you so much, everyone, for participating in this event. And thank you so much for Chamod also coordinating here. Thank you, everyone. And see you all probably in the next course sometime. Okay. Thank you so much, everyone. Thank you.
Thank you.